Welcome to this explainer. Okay, today we are diving into something that honestly feels like straight up science fiction, but it's actually a completely fundamental tool in modern geography. We're talking about remote sensing. Think of it as a kind of technological superpower. It's a way for us to see far, far beyond the severe limitations of human biology, allowing us to actually perceive the world through the invisible energy that is constantly reflecting off the Earth's surface. So, I want you to ask yourself, what if you could see invisible energy? Because the reality is, human eyes only pick up on a tiny, tiny sliver of the electromagnetic spectrum. And standard photographic systems, they also only respond to a minute portion of the total energy constantly bouncing off all the objects around us. The physical world is literally glowing with information that we simply cannot see. But modern remote sensing devices are built to capture this massive, unseen range of radiation. Basically, they capture the invisible. It all really boils down to this one core concept called absorptance. Simply put, it's the ratio of the energy an object absorbs versus the energy it receives. Everything on Earth has a totally unique energy signature, absorbing some light and reflecting the rest. And that signature is the absolute foundation of remote sensing. It's exactly how a satellite, soaring way up in the freezing vacuum of space, knows the difference between a dense forest and a concrete parking lot down below without ever even touching them. Okay, let's dive into this. Here is our roadmap for the explainer today. First, moving beyond human vision. Second, sensors and satellite orbits. Third, how scanners capture images. Fourth, decoding digital images. And finally, interpreting satellite imagery. All right, part 1, beyond human vision, seeing the unseen. When we talk about capturing an image, sensors generally fall into two buckets based on their data output: photographic, which is analog, and non-photographic, which are digital. A photographic sensor, like your traditional film camera, uses light-sensitive material. It records the images of objects at a single instant of exposure. Snap, and boom, you have the whole scene. But non-photographic sensors, often called scanners, they don't work this way at all. They actually grab images in a bit-by-bit form, meticulously collecting data line by line to build a digital picture. Moving right along to part 2, sensors and satellite orbits, the ultimate vantage point. Now, what's really interesting about this is where these non-photographic scanners actually live. Usually, they're on a platform hundreds or thousands of kilometers above our heads, and they generally take one of two main paths. Sun-synchronous satellites orbit roughly pole to pole. They pass over the exact same spot on Earth at the exact same local solar time, which ensures consistent lighting conditions for their sweeping tasks. Alternatively, you've got geostationary satellites, which are positioned much higher and orbit at the exact same speed that the Earth rotates. This means they stay completely fixed over a single spot, usually the equator, just constantly monitoring one vast, unchanging region. Okay, part 3, how scanners capture images. Basically, how we're scanning the Earth. So with these satellites perfectly positioned in orbit, they need a mechanism to actually collect the physical data from the ground. And this brings us to multispectral scanners, or MSS. A scanner uses this really complex system of mirrors and detectors to construct a scene, recording a series of scan lines at right angles to the flight direction. Think of it literally exactly like reading a book. Your eyes sweep from left to right across a line, drop down, and read the next line. As the satellite is just hurtling forward at blistering speeds, the scanner sweeps side to side, recording precise bit-by-bit measurements of the ground below. Which brings us to part 4, decoding digital images. Shifting from raw energy in space to actual numbers on our computers. Let's walk through the exact journey of a pixel. First, the scanner sweeps the field of view. Second, that reflected energy from the Earth's surface is obtained in a bit-by-bit form. Third, and I think this is the real magic part, that physical energy measurement is converted into a numerical value called a digital number, or DN. And finally, these digital numbers are arranged into a massive grid of rows and columns to form a complete digital image. And this brilliantly illustrates what that looks like. When you zoom in really closely on a digital satellite image, the landscape breaks apart into these tiny squares of brightness, pixels. Behind every single one of those pixels is actual data, a simple grid of numbers. An area of light gray might be recorded as a 61, while a darker area registers as a 38 or a 25. It's wild. The breathtaking image you see on your screen, it's really just a visual representation of a massive, incredibly detailed numerical spreadsheet.
So, a digital number, or DN, is just the intensity value of that pixel. Sounds super technical? Sure, but it's an absolutely crucial concept. When scientists and geographers engage in digital image processing, they are really just doing numerical manipulation of these exact values. They're using advanced math to pull totally unseen details out of the landscape, filtering and adjusting those numbers to reveal everything from crop health to hidden fault lines.
All right, final section, part 5, interpreting satellite imagery, making sense of all those pixels. Whether we realize it or not, we identify stuff in our day-to-day lives using a very specific set of characteristics. Geographers use these exact same tools, called elements of visual interpretation, to decode satellite images. These elements include the form or shape of an object, its size relative to others, its location, its relationship with surrounding objects, and, of course, its colors. Take a look at this striking satellite image of Varanasi. When you apply those interpretation elements, the abstract suddenly makes perfect sense. The prominent blue, meandering shape on the right side of the landscape, its distinct form, color, and location tell us immediately that it's a major waterway, the Ganga River. The dense cluster of gray and white textures right next to it, sharing a really close relationship with the river, reveals a sprawling urban area. The bright red, by the way, which is heavily concentrated on the left, in this specific false color composite, that indicates healthy vegetation. It's like a giant puzzle coming together. Let's actually put this into practice for a second with this List 3 imagery map. By focusing on distinct features, we can map out an entire region. Number 14, situated in a massive dark shape, is clearly deep water. Number 13 is tracing the edge of a landmass, a shoreline. The numbers scattered in the red zones point to agricultural or forested areas, while the really dense, structured grids with blue and white, like areas 4, 7, and 9, they show human settlement and urban infrastructure. By consciously applying form, size, relationship, and color, what looks like an abstract painting of data transforms into this highly readable map of human and natural activity. So, we've traveled all the way from the concept of invisible electromagnetic energy up to satellites in synchronous orbits, down through the sweeping mechanics of scanners, into the pure math of digital numbers, and finally back to a map we can actually recognize. It's truly a technological superpower. So, I'm going to leave you with this. How will you look at the physical world differently today, knowing that right now, the energy reflecting off your roof, your car, literally your own backyard, is constantly being scanned and mapped from space in invisible numbers? Thanks so much for joining me on this explainer, and keep exploring.